Hey there, guys, and welcome back for another lecture. Today, we're going to be going over Chapter 18, Ideal Gas Law, with me, Mauricio Garcia, and
Me, Tatyanna Shanklin.
let's get straight to it.
So the objective of this video is to basically show you guys what the ideal gas law is and how we can apply it to monatomic and diatomic gases. We also want to manipulate the equation so that we can apply it to different problems. We want to be able to analyze PV diagrams and use it to our advantage and be able to use what information is on the diagram and apply it to the ideal gas law. And lastly, we want to understand the difference between isobaric, isochoric, and isothermal processes.
So, in order to understand this, we must build a foundation. So, what you might be asking yourself, what is this ideal gas law? What does Mauricio know about this, or Tatyanna? Well, I'll prove you wrong, and I know a thing or two. So, let's start off by saying that it's pretty much a hypothetical ideal gas equation of state, which can be represented as the mathematical representation as PV equals nRT. P will be our pressure, which is measured in the units of pascals. Volume will be our V, which is measured in meters cubed. M would be the number of moles that the gas we're working with. And R will be our constant ideal gas law, 8.314 joules per mole per Kelvin. And of course, T would be our temperature measured in Kelvin. Other equations that derive from the PV equals nRT ideal gas laws are the following. If we are working in a closed system and we have the same amount of gas moles and we have the same temperature, we will be decreasing the volume. That means our pressure will increase. This can be also stated as Boyle's law. P1 V1 equals P2 V2. P1 V1 being the initial state, P2 V2 being its final state. Another example of another equation would be if we're working in a closed system. If we increase the temperature, volume will also increase only if pressure is kept constant. This can be expressed as Charles' law, V1 over T1 is equal to V2 over T2. And lastly, we have Avogadro's law. V1 over N1 is equal to V2 over N2. And to sum up Avogadro's law, it's pretty much stating that no matter what gas we're working with, whether it be oxygen, helium, hydrogen, if we take exactly 1 mole of any gases in the periodic table, it should take up about 22.4 liters of volume / space, only if we have temperature and pressure kept at a constant.
So next we're going to talk about the pressure volume diagram. So we obviously want to use this to help us solve an ideal gas law problem. So as you can see, we have the initial and final states of pressure and volume. In this graph, we have 2 points, which first is the initial, second is the final. But in other instances, we'll have 3 points. And you'll see that later on in this presentation. But first, we want to talk about what is this and how we can apply it. So usually when we're given certain microscopic properties, we can use that to find the unknowns within the ideal gas law, PV equals nRT. So, for example, if we're given the initial pressure, the initial volume, and the final pressure, then we would have to find the final volume given this diagram and given the temperature and the moles of the gas. And clearly we would use that with PV equals nRT. Another example could be that we're given the initial and final pressures of, or the initial and final states of pressure and volume, but we would need to find the temperature given the number of moles that the gas contains. It just depends on the type of problem that you're working with, and you go from there through manipulation. So now that we talked about the PV diagram, we're going to break down what isochoric, isobaric, and isothermal are. So you can see the PV diagram on the left, given as a guide to see visually how these processes work. So first we have isochoric, and that process is being shown with the blue vertical line from point C to point A. And this process is isochoric because volume remains constant. So anytime you hear the word isochoric, volume remains constant. Or you could also say that the initial and final states of volume remain the same or are equal. Next, we're going to talk about isobaric. Isobaric is when the pressure is constant, or you could also say the initial pressure equals the final pressure, and that is demonstrated through the yellow line, which goes from point B to point C. Lastly, we have isothermal, which is shown through the green line from point A to point B, and that is when temperature remains constant. You could also say that the initial temperature and the final temperature are equal. Another thing to note is that within this diagram, we have 3 points. Unlike our previous diagram, we only had 2. This one has 3. And it's the perfect opportunity to manipulate the PV equals nRT equation according to what problem we're working with.
So some examples of an isobaric, like Tatyanna previously stated, is when pressure P1 is equal to P2. So this can be as simple as water boiling from your kitchen stove. So if you were to grab a pot and put in about half a liter of water and let it boil, the temperature will increase and volume will also increase. Steam takes up more room than liquid water. And boom, perfect. We just saw ourselves working with an isobaric process. Second is isochoric, and that's when volume is kept the same. An example of that is if we were to look at an ordinary gasoline engine, there's a lot of mini explosions going on inside the piston chamber. This happens when a fixed amount of volume of gasoline is introduced to the chamber. The piston then smashes down, increasing both temperature and pressure. Boom! Now we know what isochoric is in a real-life situation. Lastly, isothermal, and that's when temperature is kept the same. Now, using our last example of the gasoline engine's process, if we were to live in a perfect world, the engine will be 100% efficient. So when the gases of the engine escape, the cycle repeats itself. And if we are at 100% efficiency, our temperature will remain constant. Again, I want to say thank you for showing up to class today. It's always been a pleasure. You guys make my day. But if you have any questions, don't be scared to email me. I am here for you. My email again is mgars401@ucr.edu. And again, be safe.